Yes.
Thank you. Can we put the lights back on again?
Okay.
Or you want them off? Yes.
Well, it's up to you. Do you want to fall asleep or not? So can you hear me? Well, it should be fine. Okay. So thank you everyone for coming to my talk, and I want to thank the organizer for having me today for the talk. And personally, I don't really know Fred Holman myself. I don't have the chance to meet him, but well, and also I'm not a grad student in computer science, but still I have some time. Well, I have at least half an hour to talk to you about math. This was my half hour. So this is my talk today is about quasi-flag manifolds and moment maps. And I will start from groups. And this is time I do start from group with some constraints. We'll actually work with finite reflection groups. So this is basically the outline of my talk. We have, well, I guess five components. We'll start with what is the definition of quasi-invariance of finite reflection groups. I give you the algebraic description. I give you some examples, some of its algebraic properties. And the question we're interested in is the topological realization of those algebras. We're interested in finding spaces whose rational cohomology realize those spaces. And we will first quickly go through the example of rank 1 case that can be done very easily. But for the high rank case, it's much trickier. So I show you a sketch of the proof how things can be done in that case. We'll give you a kind of a quoted homotopical decomposition of the flag manifold to help you to see where the generalization comes from. And if I have time, I'll also talk slightly about some of the further directions we're interested in. So that would be the plan of the talk today. And I'll first start with definition. So for definitions, I want to start from very classical thing about invariant polynomials. Polynomials, they're given by, so I'll start with a finite reflection group. Think about the case like symmetric groups where X just a finite dimensional Euclidean space by permuting indices of those variables in a polynomial ring. And I'll choose V to be my representation. Well, I said it's complexified representation because it should be coming from a Euclidean space, but we take complexification of that because it's just classical place where we work with efficiency. And if you think about the usual way how we think about a polynomial being invariant is basically, well, you act by any element in the group, it does not change. We want to change slightly how it's defined. We are looking at not just, well, in fact, you don't need to look at everything. You just need to look at where the reflection acts. And if a polynomial is invariant under all the reflections, we know it's because it will be invariant because all the elements in my finite reflection group, they're generated by these reflections. And it turns out there is a very classical theorem by Chevalier, Shepard, and Todd that these invariant polynomials, they're also polynomial algebras themselves. And the polynomial ring itself is a free module over this invariant polynomial of a particular rank, which is equal to the size. Yes?
Could this be a complex reflection group?
Yes, good point. The reason I call this theorem because it actually works not just for finite real reflection groups, it also works finite complex reflection groups. But I'm not going to talk about those cases, even though a lot of things, and in particular, quasi-invariants can be defined over those. But I'm not going to talk about them in today's talk. We'll focus on the case of finite reflection groups that actually come from the Weil group of Lie groups. So that's why I'm not going to talk about story in complex direction. And now we are going to do a slightly generalization of the definition to get the definition of quasi-invariance of finite reflection groups. So this is the case where I do the generalization instead of, so instead of requiring after applying these reflections, I get something that's the same as whatever I started with. I require the difference to be in the same class up to some powers of a linear functional. So this is a linear functional that defines my reflection hyperplane. This will also be my root in my root system associated with this finite reflection group. So this will be the definition. And in order to do that, I need to choose a power of this principal ideal. And that with what we call the multiplicity. And this multiplicity is assigned for every reflection hyperplane. I will assign a particular integer value, in fact, natural numbers. And we want this assignment to be doubly invariant. And doubly invariant is essential for this definition to actually give me If I try to look at all collections of quasi-invariants, they actually form an algebra itself. If I don't have this doubling invariant condition, they won't. They will just be a vector space. So this will be my definition. And in particular, there are two special cases, two extreme cases. When my multiplicity is designed to be 0, this is just everything. And I've allowed my multiplicity to be infinity. And the way I think about it will be just taking intersections over all multiplicities. This will give me recover just all invariants. So this is the kind. So quasi-invariants, they just lie in between all of them. So that would be a definition. And to help you to see things, I'll give you two examples. First example is about the rank 1 case where my W is just C mod 2. I act on a one-dimensional space by reflection along the origin. And this is a case where, This is a case, I start with a polynomial in one variable, and everything in the middle, the actual polynomials generated by x squared, which are the invariant part, and some higher power terms corresponding to the way how we define quasi-invariants. And if you take the intersection along all of them, at the very end, you reach just invariants. And one thing that would be easy to see for this particular case is you see all these quasi-invariants, they're algebras, and also there are free modules over these invariant polynomials of the rank equal to the size of a Y group. So this generalizes the classical results for m equals to 0. This, on the other hand, won't really be very easy to see when you move to higher rank cases. Here, I'm giving you one example. If I look at the rank 2 case, let's consider my Y group to be just symmetric with on a set of 3 elements. And view it as a dihedral group, so it acts on an R2 with 3 configuration lines. And this is the case if you try to do explicit computation, you can check my invariant still is a polynomial ring with those 2 generators. But if you try to unpack definition of my quasi-invariant with multiplicity assigned to 1, so this is 1 for each one of the reflection hyperplane. And you can check this is a module with very complicated description of generators. It still have 6 generators, which is equal to the size of my group S3. But in general, finding the, for example, showing that this is actually, again, a free module of the same rank is actually a very difficult question. You need to use a lot of techniques. Well, you can either do it combinatorially or you need to use representation theories. And in particular, you need to use representations of rational Chladnick algebras to do it. We're not going to go into the mathematical physics part of the story, so we skip it. But in general, we have the following theorem, which is about, indeed, well, not just for these finite reflection groups, but in general for finite complex reflection groups. And any multiplicity that's given, those quasi-invariants, they are indeed free gradient modules over invariant polynomials still of the same size. This will be a very non-trivial result. Fagan and Veselov, they proved this for dihedral groups in 2002, and Barrest and Ettingolf and Ginsburg, they proved it in 2003, and Barrest and Charlock, they proved it in 2011 for the case of complex reflection groups. So that would be, yes.
Again, so I'm surprised that the multiplicity wasn't entered into the rank.
Yes, it won't change, and that's very, very important. So those, let me make a remark here. Like even, and I think one you can kind of, well, not really see, but from those examples, this is the S3 case. You see, oh, sorry, this is, I move a bit too much. This is, oh yeah, just right here. It won't really change. You have the shift, but the number of elements in the rank remains the same, no matter what kind of multiplicity you're working with. And this is in general very difficult to prove. So, and also another remark is all these quasi-invariants, if you think of them, because they're commutative algebras, if you think of them as varieties, well, these CVs, they're affine varieties, they're very nice, smooth varieties, but quasi-invariants themselves, they're not smooth. They have singularities, but they're the type of singular variety that behaves not too bad. In fact, they're called Macaulay, and they're even better than that. They're Gorensteins. So they're kind of the nice, the singular varieties that you can. Yes. Yes.
A lot of us know that these actions are homogeneous, so you have a grading on everything?
Yeah.
So you're saying no matter, okay, no matter what, M, whatever M is, you have the same rank. All other gradings will have.
I think it's not turned on.
Oh, okay. So you have for each multiplicity, it's always a free graded module of the same rank.
Yes.
So are the generators in the same degrees, or are the degrees of those generators changing?
The degree will be changing. There will be a shift, and you will see. Well, I didn't put it here, but if you try to look at the Hilbert series, you will see they have a shift. The degree does change as M increases. They actually become bigger and bigger when M increases, and that also kind of makes sense because you know that in the limited behavior, they're all gone because in the limit behavior you just get invariance, so everything should be gone. So that's kind of behavior for those quasi-invariants. So that's all the algebraic story that I want to briefly show to you what happens in those algebras. And I want to move back to topology. So I want to do these topological realization problems of quasi-invariants. So well, if you just look at the question of realizing those algebras is not well, theoretical speaking, they exist by Coulomb's rational homotopy theory, but we are interested in more than just realizing every single space. These collection of quasi-invariants, they do have more structures when we put them together. For example, if you look at here, if you try to look at the multiplicities, there is a partial order on the multiplicities by just comparing each of the multiplicity assigned to each of the reflection hyperplane. And
how is the W quantified?
Oh, sorry, W is the Weil group. Sorry, finite reflection group.
No, but what, it's just, you're assuming it's a Weil group.
I'm assuming, well, I'm assuming W to be a finite reflection group, even though I'm only interested in the case where W is a Weil group of a Lie group.
Okay.
Yeah, that will be the case.
That's
That's the case. Because you'll see next slides that where I'm interested in those particular cases. So because we have this pole set of W invariant multiplicities, we actually put them together to form a category of diagram of pole sets. And if you try to look at the corresponding quasi-invariants, they actually assemble into indeed a diagram, but it's in the opposite direction. Well, I put it here, commutative algebra. Well, it depends. You can think of them as commutative algebras. If I want to do the topology realization, I should think of them as graded commutative algebras. But I put the commutative algebra here because, well, I mentioned the variety of quasi-invariants and the two ways when you think about them, whether it's graded or ungraded. Just that side remark. And this diagram has the property that each of the space, they are indeed equipped with the W action. So this is not just a diagram, it's actually a W equivariant diagram of algebras. And we have these two extreme cases, 0 and infinity, and everything else just lies within between. So this is the kind of whole diagram structures we want to realize. So not just every single one, we also want to get a kind of very nice compatible collection of spaces so that not just the rational cohomology realize those algebras, but also they're compatible with the diagram we have here and also the W action here. So that's our goal here. And the starting point comes from a classical result from Borel, which is, well, first question, we have polynomial rings. Where do polynomial rings come from? They actually come from the rational cohomology of classifying spaces of Lie groups. Of course, that's not only case, but we are starting from here because they're a very nice result from if we have a compact connect Lie group and a maximal torus in it, the natural inclusion of the T inside G actually gives us a map from the classifying space BT to the classifying space BG. And this vibration actually gives us a monomorphism on rational cohomology, which gives us precisely this embedding of invariant polynomials inside all polynomials. And that's precisely two extreme cases we have for this collection of algebras. So we have our starting point, at least for now. The question is, how do you fill in all the spaces in the middle in a systematic way? So let me formalize this realization problem. Here it is. Basically, we want to construct this collection of spaces, as I just explained. The first step is BT. The limit behavior is my BG, and I need to fill in all the spaces in the middle so that each space, because we require those algebras, they have W action. We want our space to equip with W action. And the maps on the algebra side, they are W equivalent. So we also want the map on the spaces side, they're also W equivalent. And we want the homotopy colimit along this diagram. Forget about BG part, just the diagram on top. It actually is weak homotopy equivalent to BG. And also we have, well, there's one thing, property I didn't mention. If you take invariants of those quasi-invariants, they are still just all invariant polynomials. And we have on the side of topological space, what we want is try to look at the homotopy W orbits of those spaces, so that when we try to look at equivalent homology of those spaces, they still recover just BG. So that's what we have. And the last two properties about, well, they really realize those quasi-invariants. And the result that we have is that we can construct diagram spaces for those multiplicities in a very functorial, nice way, satisfy all the properties except for the last two properties. They're satisfied at the level of even dimensional cohomology, but they do have non-vanishing odd dimensional cohomology. And here I put a grading for those polynomial generators to be degree 2, so everything will be 2, even so that the classical quasi-invariant, they should be think of as graded commutative algebras concentrating even degrees. And we actually can construct spaces where we can get diagram spaces whose even dimensional cohomology realize those spaces, but they do have non-vanishing odd cohomology in those cases. So that would be the kind of realization problem and the result we get. And let me show you first the case of rank 1 case, the case of Z mod 2. So this will be given in a slightly different form, but we can quickly show it here. This is the case, I'll take my G to be SU2 and with a maximal torus in it. This is the case, my W action is actually given by reflection, it's actually given by sign change on my variables in my polynomial ring. And it turns out in this case, if we do a kind of join construction, this is a Gannett construction, in fact, and we can do it iterative many times. And if we do the M iterative joins on these spaces of G quotient D with G, we actually can get, well, we actually can get those spaces equipped with the G action. If we take its homotopy quotient by the G action, this will be the space which satisfies the result. You can do the computation and check this is true. And this fits into a diagram. So if you were here last week, for the mini course, you actually have seen these Gannett constructions. I'm missing one arrow here. There should be one more arrow here. But this, if you do this Gannett construction iterating many times, they will everything's space in the middle. These tower spaces actually solve this realization problem, and they solve the problem not just for even dimensional cohomology. Those are the spaces where they do not have all dimensional cohomology. But this is kind of very special case when it's rank 1. And I told you it's very special. Now you can ask the question, if I want to do it for higher rank, maybe I can just iterate this Gannett construction and see what I get. And turns out I can do that. It won't really give me something that's very nice. So we want to make some modifications. And in order to do the modification, we need to look at some more complicated diagrams or graphs that we're interested in. So let me first introduce the Brouillard moment graph associated with, associated with the flag manifold. And this will be basically, this will be a graph with, a Brouillard moment graph. For simplicity, it corresponds, we have a simple unoriented graph, where in this particular case, our vertices will correspond to the elements in my Y group, and my edges will be pairs from one Y group to the other, provided there's a reflection moving from one to the other by multiplication on the left. And we can use this graph to produce a pole-set face category where my objects are both the vertices and edges in the graph. And morphisms are, the non-identity morphisms are given by the arrows pointing from edges to the vertices if this edge connects those vertices in the original graph. So let me give you one example. Again, for the case for my Y group equals to S3, this is my Brouillard graph. And so there will be 6 elements correspond to elements in my Y group, and I have those connecting edges. And I color them with different 3 colors, and the same color corresponds to using the same reflection to connect those 2 edges, and 2 vertices. And if you want to create a face category, it's just by replacing each of the edge by an object and connecting those. So this is where how you visualize the face category associated with the Brouillard graph. And there is actually a geometric interpretation of this graph, which is given by looking at, if I start with the flag manifold, for example, the case of type N, I look at GLN. So in this case, instead of compact connect Lie groups, I look at the complexified version of it. And I try to look at the Borel subgroup in it, which contains my complex torus. And we actually have a homomorphism between the compact model of flag manifold and the flag variety. And if you try to look at these, look at flag varieties, the Brouillard graph actually gives you the structure of the 0 and 1 dimensional complex torus orbits inside the flag variety. So my vertices are precisely the fixed points inside my flag manifold. And also my edges are corresponding to the complex dimension 1 orbits inside the flag variety. So that would be the kind of correspondence, and that's the geometric interpretation of the graph. And we are trying to do a kind of thickening of that. So here is the way we are going to decompose the, we're trying to find a homological decomposition of the flag manifold. And we call it a manifold. In fact, it's just a space. It's not really a manifold. So in this case, this face category is actually equipped with a W action. You don't need to worry about the W action, but it does exist so that you can look at this. C gamma is actually not just a category. You can view it as a category from the one point. I don't know how to use this pointer now. Yes, here. So viewed as a functor from the category of W, viewed as one object category, morphisms are given by elements in my group as this functor. And therefore, by Thomason's results, you can actually form a homotopy quotient. It's actually given by just the growth and deconstruction of this functor. And you can use that to construct first a functor from C gamma to topological spaces, just mapping vertices to fixed points, edges to one-dimensional orbits. And we want to extend it to a functor on this homotopy quotient, so C gamma HW. But in order to do the extension, we need to tensor by G cross W. It does not exist on the original just orbits, but it does exist. We do this extension, and this is a functor to G spaces. So that's what we have. And that's, I put a little 0 here, and because that's the initial step, that's actually for multiplicity equal to 0. And turns out if we try to take just the homotopy colimit of that functor that we have, we actually will get a G equivalent mod P cohomology isomorphism for those 2 spaces for every prime except for P equals to 2. It also works for rationals as well. And those spaces we try to compute, those F0, they are not simply connected space. So we have a kind of version of correction. We call this T plus construction. It's kind of similar to how, well, not really similar, but kind of philosophically similar to how Quillen defines this plus construction to kill the fundamental group. We also have a categorical way to kill the fundamental group to get such a space. And so that we have a simply connected model of those spaces, and they will, and we have, and those F0 and F0 plus, they will be mod P G equivalent mod P cohomology isomorphic to each other. So this is the modification we do, and this will be the initial step. I'm running out of time, so I'm only giving you a sketch of how we are going to do the construction. Roughly speaking is, well, we start with this C gamma, this will be initial step. We replace it with the thickened category. The way we do the thickening is by, we still fix the fixed points to be whatever the fixed point we have, but we thicken those edges to be the barycentric subdivision of a of a simplex. And we use that to construct a new category, which we call the CM gamma. So it's the category associated with a particular multiplicity M. And we construct, similarly, we can construct a functor from CM gamma and extend it to a functor from CM gamma HW, the homotopy quotient, to G equivalent spaces. And so that when we take the homotopy quotient, the homotopy colimit, we will get a space. And this is precisely the space what we call the quasi-flag manifold. And as you can hear, I'm taking homotopy colimit. They're actually homotopy types. We do have models, and they're not manifolds. I know it's a bad name, but classically we have this quasi-flag. We have flag manifolds, so because they resemble the quasi-invariant case, we call them quasi-flag manifolds, even though they're not. This is a very bad name, but that's what we have. And then we apply again a similar universal P plus construction to obtain a simply connected model of the spaces. So this is what we have, and these are the spaces that we get, which gives us the solution to our realization problem. And if you remember, one of the conditions I mentioned is that we have a W action. We require there is a W action on the spaces. I'm not mentioning it here, but I'm making a remark that if you try to look at construction, we have here, there is indeed another W action, which commutes with all the constructions we discussed before, and therefore they will actually induce a W action on the final homotopic limit we constructed. And that is precisely the W action we want on the spaces that induces the W action on those quasi-invariants. So that will be the construction, and that will be the final remark I have. And I think I'm running out of time, so I don't have time to explain the construction, but feel free to ask me questions and I can explain a bit more. And thank you for your attention.